Okay, so again, test is Thursday, which means you already have the review. I'll put up the answers later today. Tomorrow we'll mostly do nothing new, just go over questions on it. So like the first test review, it might be a short class. And again, if you're going to take it at a different time, for whatever reason, you're going to send me an email with a possible other time. A little thing is this is about the time of the semester last semester when everything went online. So if you look in the folder under the spring folder, you'll start having notes about this point. So in some ways, there are now two sets of notes you can sort of look at. They should overlap a lot, but they might have a few different examples and so on. And same thing if you go to the YouTube channel, there will be the recordings for the spring classes also. And hopefully I was good and actually said what was on each of them so you can check to see if it's there. So I might go over different homework examples. Somewhat. So as I said, I'm not sure about the 3.11. And like the test 1 review, the test 2 review is longer than the actual test 2 review, but yeah, similar. So what I'm going to do today is we're going to start off, as usual, with some of the homework, in this case from 3.6. 3.8, unless you want me to, I might mostly skip because it's the same thing except now we're integrating the density function, so it's similar ones. And then I will have you do what I was going to have you do yesterday, which is just here are some problems. You're going to try them on your own for double and triple integrals. I think just triple integrals, but I'll have to check. And then we'll get into 2.8 and 3.0. See how far we get. Okay. So let me go to a new slide. So hopefully maybe I'll be able to fit the whole thing on. So they're giving a really basic function. Oops, I lost. I'll put it in a second. I have to be more specific about the sphere. So the sphere is this, and the cylinder is this. A little technical thing is I found that last week when I was speaking with the microphone, it was getting static. So I'm trying this with the built-in microphone. So let me know if something comes up and I'll try switching back to the microphone. So we'll see. So this one, as usual, I can't easily draw it, but you can kind of see it. We have the cylinder, and then it just goes from the bottom of the sphere to the top of the sphere. So if I was looking at it from the front, so if I let y be 0, I'd have the sphere. It's almost a sphere. And the cylinder as it looks like from the front. So this is z, this is x. So letting y be, for example. And this section is looking at spherical and cylindrical coordinates. So the first question is, which do we use? And since we're looking at both the cylinder and the sphere, it might not be obvious. So the first thing to check is, well, let's try spherical, because at least the outer part is a sphere. And for that, what we have to do is say, well, what happens if I have a typical radius? So if I start at the origin, if I go here, I'm going to go straight to the sphere. On the other hand, if I look at this part of the region, I'm going to hit instead the cylinder. Which means, would I be able to do this with one integral? No. So if I'm using spherical coordinates, I'd have to break it up into the two pieces where it changes at this point where this cylinder hits the sphere. Also, if you think about it, if I had this and I want to put that into spherical units, well, that would be x is equal to rho sine of phi cosine, oops, that's a phi, cosine of theta squared plus y is rho sine of phi sine of theta squared. So it would become that. So the first two parts are the same, rho squared sine squared, rho sine squared, and then cosine squared plus cosine squared, which is 1. So it does simplify a little bit. But you can see it's not going to give us anything nice in terms of our limit. Right? We're going to get a cosecant of phi. So cylindrical isn't very nice. I have to split it up. When I do something for it in terms of the cylinder, I get something not very nice. So instead, I'm going to do it in terms of cylindrical coordinates. And as I often do, I'm going to split that into two pieces. Which is I'll just leave z as it is. And I'm not sure I gave myself enough space for the limits, but that's okay. And then we'll deal with the projection in the second part. So looking at this, and I've already messed it up, so let me draw it over here. If I draw a typical line, what is the bottom and top function? And you can see it's where it hits the sphere. So if I solve for the sphere in terms of z, I get, and let me start with the easier one, the 4 square root of 4 minus x squared minus y squared. And the bottom is negative. Right. And of course, I could really get, since the function is just 1, which means I'm just getting the volume, I could start at 0 and then double it. So if you want to get rid of the bottom limit. So then we want the projection. In this case, it's pretty obvious. It's just the cylinder, which is therefore the circle. And therefore, we're going to change it into cylindrical or polar coordinates, which means looking at this, what are the limits? And I'll put in the third and fill in the third integral in a bit. What are the limits for? Let's do it. dz, dr, d theta. Limits. Put in. So r will go from 0 to 1, and then 0 to 2 pi. In some ways, I just want to look at it from the front because I can't easily draw the cylinder inside of a three-dimensional sphere. So just the only reason I did is I can't do the three-dimensional drawing. And there's nothing special about y. I could just easily let x equal 0 or z equal 0. I just wanted to look at from any side, which actually I didn't want z equal 0 because that would be from the top, but either x equals 0 or y equals 0 so I can see what's going on. So yeah, nothing in particular. And then for the inside one, we're going to have to rewrite this. Yeah, so in some ways that's what I was going to ask. I'm going to say we're going to fill in, which is why I left room, is we're going to have to get the extra r for the polar coordinates. Is that what you were talking about? Yes, okay. So I was specifically waiting to ask about that, but yes, we're going to get the extra r, and then we have to rewrite the inside limits. So what is the inside limits in terms of r. And obviously it's going to be plus and minus, so plus and minus and square root of what? Yeah. And again, since we're doing 1, we can go from 0 to and just do the top half and then double it because we're getting the volume. So in theory, we could also do it with spherical, but you can see with spherical, it would be a pain. Okay, so any questions on this? So I should make it obvious here's our final answer. And there how to actually do it, but as with the quiz, I'll probably have you do one integral and then just set up most of the other ones. Right, so cylindrical are just, you leave one variable as it is, and the other two become polar. So any other questions on this? Okay, so let me do one that is spherical and start with the basic one. Again, in the background, unless I say otherwise, spheres I'm going to talk about will always be centered at the origin. So this is the x squared plus y squared plus z squared is equal to 1. And I want to get the integral of this function over that region. So as I said, this is kind of basic one. So in terms of the limits, I'm not even going to bother drawing. I'll leave a lot of space for the stuff here. So if I do d rho, d phi, d theta, then where does rho range from? Right, 0 to 1, because we have just part of the sphere, so the radius is just going from the origin all the way out to the sphere. Phi will go from, and this is where the first octant comes in, phi will go from 0 to pi over 2. That tells us we're only looking at the top half of the sphere. And what would be d theta? Also 0 to pi over 2, which tells us now we're just looking at the first octant. So the middle one tells us we're just looking at the top half. The left one tells us we're just looking at the right half. So between those, we get just the first quadrant. And now we put in each of the different things. So we put in x. X, as I did quickly in the last one, is the rho sine of phi cosine of theta. So that's x. Z is rho cosine of phi, z. And then we always get this as part of the conversion from dz, dy, dx. So x, x, and z, and the conversion factor. So this one we didn't have to draw. This is kind of the more a fairly straightforward one, but any questions on this? So this is using the few conversion things. Oh, because first octant says we're only in the part of the three-dimensional surface where x is more than 0 and y is more than 0 and z is more than 0. So this one I wasn't going to draw, but I mostly can, which is it's saying here what we're looking at is, no, I can't. It's saying I can draw, but you can see how good my art is we're just in the first quadrant, which is just x is more than or equal to 0, y is more than or equal to 0, z is more than or equal to 0. And since phi is measuring from the positive z-axis, and since we're only going down to the xy plane, that's telling us we're only going from 0 to pi over 2. Because you remember from yesterday that if we go from 0 to pi, that's giving us the whole sphere. I forget. Let me see if I think it's geograph, but as I said there, when I choose this one, I just chose one that was one of the top ones. So yeah. And the thing it says 3D calculator, but then I think officially it's GeoGebra 3D calculator. But as I said, when I was looking up, there were a lot of them, and a lot of them got pretty good ratings. So almost any of them will work. And it'll let you graph it, and then it'll let you rotate around so you can see it from different angles. So you can see this is just a sphere. So when we're looking for rho, we're asking if I draw. So if I start at the origin and draw a typical radius, where does it hit? And here there's no constraints, so it just keeps going until it hits the sphere. And it's a sphere of radius 1, so we go from the origin, which is radius 0, or rho is equal to 0, to the sphere, which is rho is equal to 1. So this one is just a fairly straightforward one, so no constraints. Looking at it, if we were actually trying to do this, this might actually be a bit of a pain because we have a sine squared and a cosine squared, but that's a different story. Okay, so any other questions about the setup? Okay, so let me do a couple others. Let's jump to 26. So this one and the next one are just saying, here's an integral. Do it however you want, but you might want to convert it to either cylindrical or spherical, pretty obviously, since we're in that section. So the question is, what does this look like? So looking at these two, what is this 3D object? Right, so it looks like a circle. And the fact that, so this, we have the y equals, just using the top limit. Certainly looks like a circle. And then the -3 and 3 go with that, because that's just what happens if I put in y equals 0. I get x equals plus or minus 3. So the first two look like it's a circle. The fact that we're now in 3 dimensions and we have this means what are we actually getting? Right, a cylinder. So we have a circle we're letting then go from z equals 0 to 5, which means we're going to get a cylinder, the circle going from 0 to 5. So we're getting, and again, I can't really draw it, but something like that. And obviously, therefore, we should convert this into cylindrical coordinates. Okay. So the only question is, which variable are we going to leave as is? Which hopefully is obvious. So do we want to leave y or x or z as they are? Z. Right, we want to leave z as it is because you can see that the first two integrals, the ones here, are what forms a circle. Y is in terms of x, which means x and y are the ones that form the circle, which means those are the ones we want to make polar coordinates. So I'll leave the z on the outside. That way we can just leave it as it is. But then we're going to become r, dr, d theta, and then dz. Oops. I should have left myself more room. So z will stay as it is. X squared plus y squared becomes r squared. And then we get, which I already put in, the usual r. And given that this is a circle, what are the limits for r? So the inside, 0 to 3. You can see it's a circle of radius 3. And given that we have these lower bounds, do we have the full circle or just part of it? Right, so 0 to 2 pi, the whole circle. So any questions on this? Right, so in some ways that's why I'm sort of trying to write here, which is that looking at this top limit, that's y equals 9 minus x squared, which gives us a circle. And the fact that the z's are just constants is telling us that we're not doing anything with z. So I'm just doing a circle at any value of z. So I'm drawing the circle, and that's what I tried to draw. Right, here's x squared plus y squared is equal to 9 when z is equal to 5. Here's x squared plus y squared is equal to 9 when z is equal to 0. And then everything else is everything in between. So this is kind of a typical cylinder, which is at least a right circular cylinder. When you have two variables that form the circle, and then the other variable you let be whatever you want. Yes, right. So if the limits are constants, it's not really going to change much if you flip the order. So the only time you really, so for example, in this last one, I got a dr, d theta, dz. I could pretty easily flip the order and make it d theta, dz, dr with the same limits because the limits are constants. What happened to the first limits? What do you mean? If you mean, do you mean these limits? Right. So the idea is when we're converting to either circle or cylindrical, since we're now looking at the thing in a different way, we have to see what it is and then convert it, because you remember that this is a circle. Right, that's a circle. In polar coordinates, that same circle is that. So by making it a circle, we have simplified it into a much easier equation. And so that whole equation becomes just, so this r equals 3 is the same in polar coordinates as those two limits in rectangular coordinates. That's the whole nice thing about it, which is if we have this circle, it becomes a constant. Okay, any other questions? Okay, so let me look at the next one. 27, I think, was the next one. Yep. Oops. So same thing. Here's an integral. We want to actually do it, and so we want to see if we want to convert it. And as I said last one, you're good to, because this is on spherical coordinates, and the question is, which do we want to do? So again, we look at it. So I take this top limit, say, which becomes z is equal to square root of 20 minus x squared minus y squared. Which is this. What is that? Because that's a sphere. So far it looks like we might want to try spherical coordinates, but as one we did a couple ago, might not, depending on what the other limit is. And so this we can do it one of two ways. One is you recognize what this is, or you try putting it into spherical coordinates to see if it works. So first, what is this? So that's a cone. If you don't recognize it, if you try converting this into spherical coordinates, you would say, well, z is equal to rho cosine of phi. And I always go through polar coordinates, but you don't have to. I know x squared plus y squared, and polar is r squared, so this is 2r. And then I know that r is rho sine phi. So the rho's cancel. And if I divide through by cosine, I get the tangent phi is equal to 1/2, which means its phi is equal to whatever that angle is. So this is a cone, but even if you didn't recognize it, if you tried solving it and say, oh, this is really easy, it's just phi is equal to a number. So we should probably use spherical coordinates. The only little thing is, we look at the projection, and what is the projection of? So what is y equals square root of 4 minus x squared? So that's a circle. And in a seemingly big thing, it has a radius of 2, whereas the radius of the sphere is square root of 20. So we have this little question, do they go together, or do we have another cylinder involved somehow from these first two? So let's check to see what happens when we put the two limits together. So I have z is equal to the sphere and z equals the cone. If I put them equal, what do I get? So I start writing on myself. So obviously I'll square both sides. I get that. I can then add the x squared plus y squared to the other side to get 5. And trying to keep this all on the same page. If I then divide through by the 5, I get the circle of radius 2. So where the cone hits the sphere, which is the biggest part of it, is at the circle of radius 2. So the inside integral look like they might be different, but it really just comes from where the cone hits the sphere of radius square root of 20. So let me stop there for a second. Well, so one is I know we're going to need it, but the other is just notice I'm just checking. So this part I want to know, is spherical coordinates going to be okay with this? And so I want to solve that. I found that that equation is the same as this equation, which is a really simple equation in spherical coordinates, which means it makes sense to use spherical coordinates. Then we'd be getting something weird, which we wouldn't easily be able to do, because the idea would be, suppose we got that this was square root of 1 minus x squared. So we, with the cylinder of radius 1, then we'd have to break up the integral, because part of the way we'd have the cone, but then as the cone's getting bigger as it goes up, it would then stop at some point and become a cylinder. So we'd have a cylinder on top of a cone, and then where it hits the sphere. So we have to break up the integral into two pieces, and because we have both cones and both cylinders and cones, neither cylindrical nor spherical coordinates would be very good. So it would be a ping, which means you really aren't going to see one like that. But yes, you'd have to break it up. So in other words, when you see this, that should be your first idea, which is that that inside one probably comes from where the cone hits the sphere, because otherwise it's going to be a much harder problem. So any other questions before I do the integral? As I write it, I'm going to ask you one other thing. So we have z, so we're going to do spherical coordinates. So z is the rho cosine of phi. As always, we get the rho squared sine of phi. So again, as I did yesterday, cones are nice for spherical coordinates because it's like just a wedge, because anywhere in that cone, if I start at the origin and follow a radius to the circle, I don't hit anything until I get the circle, which means I'm getting the full range of radiuses, which means the limits for the radius for rho here would be what? So I start at 0, and I go all the way to the sphere, which has a radius of, not very nice, but yeah, the root 20. Before I get to the other two, let me go back here, because we said that the projection was a circle, but the question is it the full circle? So what does this tell us? Right, it's just going to be the upper half of the circle, which will come in a second. So what is phi? Phi goes from where to where? One we get from the cone, which is one of the reasons I did this. And so the only question is at the top or the bottom limit. Right, so 0 is the bottom, and that's because, again, phi is measuring from the positive z-axis, so we're measuring down from the top. And now, since it's just the upper half of the circle, theta goes from 0 to what? Oh, that's because of the 0, because if we wanted the full circle, we would go from the negative square root to the positive square root. So if I was drawing this part here, this would tell me I am going all the way from the negative 2 to 2, but only in the top half. And therefore from 0 to pi. So if that bottom limit in the middle and the original one was negative square root of 4 minus x squared, then we go 0 to 2 pi. No, because think about, suppose we wanted the area in the upper half of the sphere from the xy plane to the cone. Then we will go from inverse tangent to pi over 2. Right, so the phi value is, this is the z-axis, and v is the measure down from the positive z-axis. And in some ways, the one question for Keenan is, the next problem I'm going to do, the limits will not be 0. One of the limits will not be 0, and you'll see how that works. Often it's 0 to something because otherwise, as I said, the picture isn't nice. If this is the cone, if I ask for what is this, integrate over this region, then we go from the tan inverse of 1/2 to pi over 2. And you can see that's, I don't know, what is that, a bowl or something like that? So any other questions on this? Yet another. In some ways, I know the spherical coordinates and so on are kind of a pain, so let me do a few of them. 36. So let's find the volume of the region between these two cones and inside the sphere. So as usual, I can't easily draw this sphere, so let me just look at it from the front, just so I can actually draw it to some extent. So here is imagine that's the three-dimensional sphere. I have the one cone, and then I have the other cone. And purposely not worrying about if that's where the angles really should be or not, so this is not the scale, because we're going to have to figure out what those angles are. And now rotate this around, think of it as a three-dimensional object. And we want to find the volume of that thing. So first, it should be obvious that, again, spherical coordinates are going to work nicely, because any place in this region, if I start at the origin and draw a line out to the sphere, it doesn't hit anything until the edge. So the two pairs of lines are the two cones, and the shaded region is the region in between the two cones. So as with the last one, we want to get the angle. So you can see this is in some ways a nice version, because you can see, well, it's the whole round region. So we know theta is going to go from 0 to 2 pi. It is, as I said, nice in terms of spherical, because any radius I draw is only going to start at the origin and hit the sphere. So rho is going to be fairly nice. The only thing we need are, what are these two angles? So let's do each of them. So z equals x squared plus y squared. We basically did the last one, which, as I said, well, this is z is rho cosine of phi. I again do the middle thing, which you don't have to do. I know x squared plus y squared is r squared, so the right becomes r, which is rho sine of phi. And so when I divide through by the cosine, I just get tangent is equal to 1. And therefore, this is a nice one. Phi here is pi over 4. So there's one of the angles. Let's do the same thing. The other one, the only difference is that now we have, my 3 again gets messed up, square root of 3. So when I solve for tangent, I get tangent of phi is equal to square root of 3. And that actually is also a nice one. What is phi in this case? Pi over 3. So again, cones in spherical are nice. A cone in spherical coordinates is just phi is equal to a particular angle, which you just draw a line going from the origin out at that angle and rotate it around to get the cone. So you'll see often in the text and in test reviews and so on, if you go into old semesters, there's a lot of cones in spherical coordinates because it's pretty nice. Here we're looking at the volume, so we're just integrating 1, but we still get the usual spherical piece. Where rho goes from zero to 1. Phi goes from the 2 angles we did, so we just have to put the smaller angle first. And then theta goes from 0 to 2 pi because there are no restrictions. So in general, spherical are kind of a pain. The nice thing is, the only reason you really want to use it is if you have spheres or cones, which means you're not going to see too many besides those couple examples. So not the full sphere, but there's no restriction in terms of it. So if I was graphing this, if I try to make this 3-dimensional, maybe all the way around, because notice we don't have the bottom half here. So it's not the full sphere because we're not doing the bottom, we're just doing the top part. But it is all the way around. So any other questions on this? Okay, so what I was going to do now, I was going to do this yesterday, which you'll see the notes are going to be 6-1 problems. But we didn't get to a place where I would have you try until late enough that there wasn't really time. So let me now have you look at, on your own, pretty much just more of these. So just here are just 3 other 3-dimensional ones. And you're just going to try this on your own. So this is, I think there are 3. Is that true? Yeah, there's 3. So you're just going to, and for these, you're just going to set them up. So I'm going to do like I do for these problems, which is you're just going to have 15, 20 minutes, try it on your own. And, oh, actually check. Forget if I put it up. So if they're not, I'll put them up right now. So I forget if this is on Blackboard. If it's not, I'll put it up right now. So give you 15, 20 minutes to do it. Wait, check. I did not. So let me. Okay, so I had forgotten to put them up, but they are this is also now on Blackboard. So as usual for these, you'll let me know if you have questions. And otherwise, I'm going to say nothing for 15 minutes or so. All right. Again, I can't really see things, but are people done? Yep. Anyone else? Is this enough time, or should I give a couple more minutes? All right, so I guess not a lot of response, but let's try it. So the first one is kind of a basic rectangular. So let me draw it, and then you'll give me one of the ways you could do it. This is one of the few I can pretty easily draw. So it's this thing where we also have the bounds being the coordinate axes, so the xy axis, yz axis, and the xz axis. So first, someone give me an order. Which order do you want to do it? Okay. Oh, I have two different versions before I begin. So there are two different version orders. Anyone else? Break the tie. Well, so two dz dy dx's, so let's go with that. Okay, so if I do it dz dy dx, what are the limits for z? The bottom limit is 0, and top limit is right. Right, it's one of those two. And then you can see here's the projection, just that triangle, which is at z equals 0. So we're just going to get x plus y is equal to 8. And therefore, the middle limits will be 0 to 8 minus x. And x will go from 0 to 8. Right. Oh, I lost it. Oh, sorry. Right. So a few came at the same time. So yeah. So this is, if you solve for this in terms of z, which is why, in some ways, I was thinking it might make sense to do z last, because then you wouldn't have any fractions. So the inner one is, so we set, so here z equals 0 is the xy plane, and then we just solved for z. So as I said, it sort of would have made sense to do x and y before z, because that way you wouldn't have any fractions, but it doesn't really matter. And also this one, the other reason it doesn't really matter is each of the projections, if I project into either the xz plane or the yz plane, I'm still going to get triangles. So this is kind of nice in the sense that all the projections are pretty easy. Oh, so for this, you can see that the biggest we get is in the xy plane, which means we plug in z equals 0, which gave us x plus y is equal to 8. And you can see that gives us that this is 8.80. Okay. So any other questions on this? Okay, so the other one. This one in some ways is kind of cheating because we did one similar to this. Right, so z would go from 0 to 4 if we did it dy, dx, dz, for example. So what is this? That's a cone. So as we've now done 3 of these today, if I rewrite it, it's the 3-rho cosine of phi is equal to r, which is equal to rho sine of phi. Therefore, tangent of phi is equal to 3. So again, just because I can't draw the three-dimensional thing, that's here it is from the front. Again, not to scale, badly drawn. And this is the region we want. Okay. So let's start with the limits, and then we'll deal with the rewriting it. But I should put out here just so we know the order. So what are the limits for rho? 0 to 2. Because again, this is nice. Any line I draw from the origin doesn't hit anything until it hits the sphere. What is phi going from? 0 to inverse tangent. And starting at 0 because it includes the z-axis, which is 0. And finally, for theta, it's going from 0 to 2 pi. This is kind of a pain to write, but what is, let's do the two pieces. 6y becomes 6. Actually, I think I'm just going to write it, and you'll tell me if I messed up, because it is a pain to write. Oh, there we go. Very good. 6 sine of phi, sine of theta, yeah. I'm trying to save space. That's the 6y. And then what we always get is the rho squared sine of phi. And of course, you can put that together. And then, said for the test, I'll probably just have you sum. That way it's easier to grade because they're different. Am I missing a row? Oh, yes, thank you. A row. Oh, so this part, remember, is similar to the r that we get in polar coordinates. In polar coordinates, we always get the extra r for the r dr d theta. In spherical coordinates, we always get an extra rho squared sine of phi, which, if you want to remember more particularly, kind of comes from the polar, which is its rho times r. That's just always there. Okay, so any other questions on this one? Okay. So here I say rewrite in spherical coordinates. So again, as I did the other one, let's bring each of these pieces down. You're going to tell me what each is. So what does the top limit represent? Right, so that's a sphere. And yet another of these, and this is a cone. So here we have the typical for the spherical, a cone hitting a sphere. And now the question is, does this give us anything new? In particular, where does this come from? So that's obviously a circle of radius 3. Where does that come from? is that anything new? So from the inside in, what we have is a cone hitting a sphere. So the outside limits give us anything new. So part of it is, yes, that since it starts 0, we don't have the full thing. And since it's going 0 to 3, it also isn't giving any new thing. But is it a new circle, or where does this come from? There's kind of a check that we did in the last one like this. Right. So the idea is we have to check, do we get anything new? And as I said when we did the other one, it better be that there isn't anything new, because otherwise it's a much more difficult problem. But we should check. So if I put the two equal, I do get the 45 minus x squared minus y squared is equal to 4 times it. If I bring the x squared plus y squared, I get 5 times the sum of the squares. If I then divide through by the 5, I get the x squared plus y is equal to 9. So the inside circle is coming just from the intersection of the two, so I don't have anything new, luckily. Because otherwise it'd be a harder problem. But now let's look at the lower limits. And let me ask, I don't know, I have lots of room, ask what each of those gives. So if we had the full circle, we'd have negative square root to positive square root. So what does this 0 tell us? So let me bring it down here to make it more obvious. Here's our circle. So it's a half circle, and here we have to be more exact, which is this one is telling us that we are in the top half. And this 0 tells us we are in the right half, which means altogether we're in the first quadrant when we project. So I think I'm going to move down. So the limits are going to be pretty easy. So first we have 4xz. So again, it's a pain to write. It's only just right. It's the 4 sine phi, cosine theta, and then z is rho cosine phi, and then we get the rho squared sine phi. Oh, and I never did do in one piece. Someone will fill in a second. So what are the limits for rho? Right, so again, it's nice for spherical. We're just going from 0 to the radius, which is lovely square root of 45. For phi, we're going from, and this is that what it is? Oh, this is the part that I skipped, which is z equals 2 square root of x squared plus y squared. What does that become in terms of tangent? So therefore, the limits for phi are 0 to inverse tangent of that, which I don't think is anything nice. And then theta goes from 0 to pi over 2. It's just the first. It's that lovely thing. So any questions on this? Oh, because if you go back, it's this, which is x squared plus y squared plus z squared. 45. And so as usual, the radius is the square root of it's x squared plus y squared plus z squared is equal to rho squared. So the square root of it. And in some ways, I'd like them to be both integers, but it's almost impossible to make both this an integer and this an integer. So one of them is usually going to be not a very nice one, like the one we did before. Any other questions on this? As you're thinking, as usual, after class, I'll write these up a bit better and put the answers on Blackboard along with the answers to the test review. Yes, we're in the first octave. I had to think about it for a minute. Right, so this would be in the first octave. Any other questions? Okay. So let me get at this. And go back to 2.8. And let me do an example. And we got very little bit yesterday. So let me start with that. Add on, there's actually too much extra for the section. So here's a vector or parameterized function, and that's what 2.8 is, and I want to see if it's regular. And so the basic pieces are, we need that the derivative is defined at and near 1, 1, and we need that when you plug it in, the two partial derivatives are linearly independent. So we need, so there's sort of a third part, but that doesn't really come up much. So it's differentiable in terms of u and in terms of v, and the two partial derivatives are linearly independent. So in some ways, we haven't done this very much, but I like to put it on this part, at least on the test, because it's a pretty straightforward one. So here we do the two partial derivatives. So derivative with respect to u. Derivative with respect to v. Pretty obviously, looking at these two partial derivatives, is there any place where those aren't defined? No, those are pretty basic functions. As usual, place you have to worry about is you can't divide by 0, you can't take the square root of a negative number, you can't take the natural log of a negative number. None of that comes up here, so that in terms of the derivatives, this part is fine. So that's telling us that the fact that we're getting numbers back is telling us that 1 is okay. And now we need to know, are these linearly independent? And I'm going to do this in 2 different ways for the second part. But for this part, let me just do the really easy one, which is to be linearly independent, one can't be a constant multiple of the other. Or, using the language that was on last quiz, last test, I forget which, they can't be parallel. So are these 2 vectors parallel? No. So one is not a constant of the other. Therefore, they are linearly independent. And therefore, the function is regular at that point. Well, that's what we're going to decide now. So this definitely will be on it. And now the question is, in the next part, you'll tell me how far we want to, after we do this, we'll see how far we want to go. But so this part is going to be on the test, just checking is something regular. Although I should ask, so any questions on this? Okay, so let's now see how it's used, and then quickly look into 3.11, which is, as I said at the beginning of the class, and now, give me a second, and let me drink something, and now also lead into 3.11, which I now know is not going to be on the test because we have about 15 minutes, so obviously going to go far enough to do it, even though it's a fairly straightforward thing. So, any questions on this? So this is going to be on the test. Okay. So, let me do a second way we can check to see if they're linearly independent, which will look silly in this context. Which is we can look at the cross product. And the reason I'm going to do it, even though for now it's silly, is later we will want to do this. And also here it'll let us look at what I'm going to do next in 2 different ways. So I'll skip the steps. But I get that. And the idea is, if that was equal to 0, they would not be linearly independent. So since this is not a 0 vector, that also tells us that they're linearly independent. So a little note, which is one of the things we get with these 2 partial derivatives, if we are in the parameterized form, and we'll do it with the numbers here so you can see it more clearly, is it lets us pretty easily get the tangent plane in a different way. So we don't have to rewrite it in their usual form and use what we had before. So if we have two vectors that are parallel to the plane. So we can actually go back and do test one now in a different way. We have two vectors that are parallel to the plane and linearly independent. We can write it this way. And so in this particular case, we would get, and first I have to go back and do, which I'll do here. So if I put 1, 1 into the original function, I get 2, 4, 6. That's a y. So it gives us a different way of writing tangent planes. So when we did it before, to get the equation of a tangent plane, what we needed was a vector that's normal to the, or perpendicular to the tangent plane. Now we see if we have two vectors that are parallel, we can also write it in terms of these, in terms of a parameterization. But in this case, I can write it in the second way, which is we have two vectors that are parallel to the plane. So therefore, what is this vector called? Or what is that vector's relationship to the tangent plane? It's a normal vector. And then using the x, y, and z from here, I can get our more typical way of writing the tangent plane. This and this give the same thing. So let me stop here for a second because this is the end of 2.8, the only other thing in 2.8. And let me ask, so the last slide will be on it, just checking if something angular. Knowing that putting this in will mean that you'll probably have one fewer double or triple integral. Do we want this on it or not? So I think it's 9b in the test review. Any other thoughts? In some ways, actually, let me ask this tomorrow. So for 9b, I'm going to tentatively leave it on. I think it's 9b. And then after you've had a chance to try it on your own, if you haven't already, I'll ask you again tomorrow. I'll actually do I can be a bit more scientific about this. So this one, you'll tell me tomorrow if not, but let me get into the next section, which is not going to be on the test. But any questions on this? I should say, notice if all I do is ask for the tangent plane, this is you do not need to do. That would be extra work. Okay, so let me do the usual introduction into the next section, which is not on the test. So this is 3.11. And here, what I want to do is I have 3 dimensions. Right, so not 3.11. So 3.11 had a question mark. It is now definitely not on it. So my usual great artistic skill here. This is a 2-dimensional object in 3 dimensions. And I want to know what's the area of that thing. So if I'm trying this in the regular, so I have z in terms of x and y, it's kind of a pain, but you can kind of see the idea of how we might want to do it, which is I might break this up into lots of little pieces where I'd say, well, I'm going to draw little vectors, make lots of little triangle type, rectangle type things, get the area of each little rectangle type things, and get the area of each and add them up to the usual thing. And the reason I specifically did little parallelograms, not rectangles, is I know if I look at the derivative at AB in terms of u, this is about how much the R changes if I change u by a little bit. And if I do RV, I'm going to get about the same thing, except in terms of v. So I'm going to get two vectors that are parallel to the plane. And there's plane, which means it's flat. But they won't necessarily be, because we're changing into a flat thing, they won't necessarily be perpendicular to each other. So what I'm doing is the two vectors I have here are going to be the two partial derivatives at that point. And let's go back to chapter 1. If I have a parallelogram formed by two vectors, how do I get the area of the parallelogram? Right, the cross product. And the only little thing with that is we then take the length. So going back to chapter 1, the area of the parallelogram formed by two vectors is the magnitude of the cross product, which means the area of these little pieces that I've broken up my surface into is going to be the length of the cross product of the two partial derivatives. So it works kind of nicely if we have a function in parameterized form, which is why we want to talk about parameterized form. So I do one quick example. I did 5 minutes. So example. Let's do something that's pretty easy. We don't really need it for. So here we have a cylinder. I want to find what's the surface area. The reason we don't really need it is I can unroll the cylinder, which makes it into a rectangle, and I can easily get the area. But let's do it the hard way. So since it's a circle, what type of coordinate system am I going to use? Which will tell me what the parameterization is. Polar. So for example, I could do x is equal to r cosine theta. In particular, though, r here is 4. Y, there's no restrictions, so I'm just going to let y be y as it is. And then z is equal to the 4 sine theta. So this is our parameterization. I then take the two partial derivatives. So r here is 4 cosine theta. Y 4 sine theta. So derivative derivative with respect to theta is equal to -4 sine theta, 0 for cosine theta. Derivative with respect to y, just 0, 1. Ooh, even better needle. Zero, 0, 1, and 0. Cross product. And again, I'm just going to say the actual work. We're going through it quickly. And in a second, we'll put in the limits. And then we want the length of this, which is the length of sum of the squares. And let's do it, say, d theta dy. And let me ask what are the limits. So for theta, because there's no restriction on the cylinder or the circle, it goes from 0 to 2 pi. And pretty obviously y, the limits are 0 to 6. This looks complicated, but it's not really. What does that simplify to? Inner function, what I just underlined? Is that what you mean? Oh yeah, so yes, this is, I'm trying to fit it on the one. So this is, I would then take the magnitude, which is there. And this simplifies to 4. And so if I go through it, I'm just going to get the 4 times the 2 pi times the 6, again, skipping steps, although in this case, you could do it straight. And if I generalize this, you'll notice that this is equal to, and so this I said was not. So this is equal to the 2 pi times the radius times the height, which is the surface area of a cylinder. So as I said, we didn't really need it. This one you could unroll and see as a rectangle. 2 pi r is the circumference and h is the height of the, or in this case, the length of the cylinder. So here, very quickly, the usual quick intro is what we're doing in 3.11. So what I'll probably do tomorrow is, even though it's not on the test, I will probably do 9C, but just know it's not going to be on the test. So as I said, it might be a little new material, and in this case, the new material will just be going through problem 9 and going through 9C. Okay, so that's it. So later today, I will put up both the answers for the problem session sets that we just did and the answers to the review. And then tomorrow, we'll go over questions. So kind of like the first test 1 review. So except for another problem like the one we just did, nothing new. So as usual, I'm going to stop recording and you'll let me know if you have any, stick around if you have any more specific questions.